Those components you need to know what they're responsible for. Can you just look at a circuit and if I erased everything, pretty much be able to tell what the components do or what they're for?
Yes.
You should be able to by now. Should be able to. Redraw. This is the same thing as that. I just took out non-essential components for purposes of getting a snapshot of, oh, okay, it looks just like a standard transistor circuit from the beginning of BO3, doesn't it?
Yes, sir.
Except there was a resistor here and not a Zener diode. Basically the same thing. And that voltage there is going to remain what?
Constant.
You might as well call that constant. You might as well. The Zener sets the base voltage in this one. So some things to think about. Load line. BCE, collector current or transistor conduction, are what?
Inverse.
Always inverse. If you know that the transistor is conducting more, the VCE naturally is going to decrease. They're inverse. Always inverse. Always inverse. Always inverse. Always. The line voltage. Isn't it going to immediately affect the total current in the whole circuit immediately?
Yes.
It is. If I'm taking that spigot, garden hose, and I turn it on halfway, hey, I got a certain amount of flow of water, right?
Yes,
Yes,
sir.
sir.
If I turn it on more, I've just increased the intensity, haven't I?
Yes, sir.
Yes, sir.
That's what the I stands for, current, intensity. Get it? Makes sense? But if I increase potential to the whole circuit, well, there's going to be a tendency for everything to increase. If these were just resistors, and I took that Zener diode out, put a resistor there, it's a brand new circuit, basically, isn't it?
Yes, sir.
Or that's not going to be maintained, is it? No. So we use the Zener diodes to help set a particular output, and we use the transistor to regulate that by its conduction. What's the deal with these things? So, arrow analysis. The easy way depends on you at this point. Once I go through the review, and I go through all these regulator circuits again for the third time, this is the third time you guys are seeing this stuff. If you still don't get the theory, what did I say? Make sure you know the arrow analysis. Because some might still have trouble with the theory, which it's okay. Because as long as you have I'm pretty good, you're going to be fine. But I can tell you this right now, if you know the arrow analysis, you can answer every question about each of the regulators. You can. So a line increases. The series regulator, we know that line and load in VCE, the analysis is what?
The same, sir.
It's the same, or it's direct. So the whole idea is if I'm telling you this, I don't want that increased current times a fixed load to increase the voltage drop out, do I?
No, sir.
Because that's what would happen if I just had resistors in the circuit. So I don't want that to happen. Look here, VCR1, near constant base voltage. Yeah, yes, you can come over here and you can place your leads across the Zener and come over here to this variable power supply and increase it. That voltage is going to remain pretty constant until you get about 1.5 volts. Then you'll see a very small jump, like 5.02 to 5.03. Is that a lot of change? No, you can still effectively pretty much call that 5 volts. This formula here, the line voltage, equals, I've got VCR or VRS. Now I'm just going half and half because VR1 plus VCR1, doesn't that equal source?
Yes,
sir.
Yeah. In a circuit like this, a transistor, just split it in half. This side will equal source or Kirchhoff out, so will this side. So the voltage of the series drop-in resistors plus the VCE of the transistor and the load voltage will equal source. if I increase the source, it still has to add up, doesn't it?
Yes,
Yes, sir.
Okay, so that's where the compensation takes place. Also, is this a true statement? I total equals current or series drop resistors, transistor current, and load current.
Yes, Yes, sir.
Yeah. So line goes up. All these, you might as well just draw up arrows on all of them. Make sense?
Yes, sir.
Okay. So the process, the theory again. Line goes up. I don't want larger current times load current equals bigger load voltage. I don't want that. So if you think about it logically, since this is a series pass transistor, it's going to provide more or less current to the load to help maintain the constant output. Yes?
yes, sir.
That's the deal. If you got that much right there, that's more than half the battle on this. It really is. Yes?
Yes, sir.
No, I'm looking for you. Still having trouble? Okay. It's all right. You at least have a...
No, I'm good.
Okay. So we can talk a little bit later. Okay, so just pay attention. So I don't want this to skyrocket. So naturally, the transistor has to provide how much current to the load? Or what do I need? I need less current. I need a transistor to conduct less, don't I?
Yes, sir.
Well, since this is going to remain relatively constant, even though there's an increase in line and current, this base voltage is going to remain relatively constant. The brunt of the drop is going to be across R1 on this side. The voltage drop of R1 will almost become exponential to the increase in line because this current in this branch is the same, isn't it?
Yes, sir.
Over a wide range of currents, the Zener will maintain its Zener voltage nearly constant. Could you take it out of regulation by applying too much potential to a circuit or not enough? Yes, you could, but we're talking normal operating conditions, normal.